All right, so as we carry on, this is an example of fluid statics again, formal rho GH. So we're actually going to do two quick problems here, looking at just a square rectangular tank here. It's got height h, gravity's acting downward, dimensions on the bottom are d and d, so it's square bottom. And we've designed a coordinate system where z is in the up and down direction, and x and y are shown here. And what we're going to do is we're going to combine two ideas. We're going to use something that we've seen before, which is this idea of differential force being equal to the pressure acting on a differential area. And we're going to use the formal version of our gravity effect here, our fluid statics effect, dp dz is equal to minus rho g. And remember, the reason there's a negative sign here is that gravity acts opposite direction to z, because I drew z going up. So here's the deal. What we want to do is make use of the fact that a differential force is equal to the pressure times a differential area. Well, what differential area? If we're looking for the force on the bottom of the tank, we would want a differential area on the bottom of the tank. And so, since we're going to do two examples, I'm going to call this dA sub 1 and put a little 1 there because there's going to be two of them. But while we're at it, I'd like to show you that we can turn this into vector notation. This differential area has a direction associated with it, which is called the normal vector. And so we can write here n hat 1 as the normal vector pointing out of A1. And what that lets me do is convert this equation into vector form. And so when we're done, we'll get a force vector rather than just the magnitude. So if we're going to use this, what we're going to have to do is integrate both sides, as we've done. So on the left-hand side we integrate, and on the right-hand side we're going to integrate over the area. And as you know, this just becomes the force. And on the right-hand side, we have to integrate over the area. Well, the area that we're interested in is this bottom here, which is dx by dy using this coordinate system. And so we can skip a couple steps here. Well, not really, but just jump ahead to the conclusion. 0 to d, 0 to d, because we know we're integrating over the whole bottom here of the pressure, and then our differential area dA is dx by dy. Only we want to add n hat to it, which in this case is the unit vector k hat, because it's parallel to z. Now this thing could be on an angle and it would be a little more complicated, but we don't have to worry about that right now. So now we're all set up, except that we need the pressure. This is where the formal fluid statics equation comes into play, minus rho g. And so we can separate and integrate this. dP is equal to minus rho g dz. And so if we integrate both sides, we get that pressure as a function of z is equal to minus rho g z. And that might feel a little weird. This negative sign we're not used to seeing, and if I plug in a value of h for z, I'm going to get a negative pressure. Well, the reason for that is that we've actually defined our coordinate system with z, let's scroll up here, with z pointing upward. And so this corner of the box is actually 0, 0, 0, which means we're evaluating from 0 to negative h. That's the range that z takes. And so we're going to write p of negative h is equal to minus rho g times negative h. And of course that just comes out to rho gz. We can sub that in here. So we get the force is equal to the integral from 0 to d, integral from 0 to d of minus rho g times minus h. Sub that in. And then we still have our differential area here, dx dy k hat. And if you perform that integral, you get something that you've probably been expecting. Rho g h times d times d times k hat. That's the force acting on the bottom of this tank. In the next example, I'm going to show you how to get the force on the side of the tank. We'll follow a parallel process.